Welcome back. I hope you find the previous discussion helpful in laying the groundwork for understanding how structures vibrate. Now we are moving into really exciting and practical area, experimental model analysis. As you can see, this is our seventh section of the fifth unit, that is experimental model analysis for the course ME22088, vibration and noise control. So what exactly is experimental model analysis, or EMA is often called? Well, unlike the analytical methods we might have touched upon earlier, where we use mathematical models to predict vibration behavior, EMA takes a hands-on approach. It involves actually testing a physical structure to identify its dynamic characteristics. I am Dr. Sendamarikanan, Associate Professor in the Mechanical Department at SVCE. Feel free to reach out if you have any questions regarding the topic or any other material we are covering in this course ME 22088, Vibration and Noise Control.
As we are discussing the complexity of real-world structures makes experimental model analysis incredibly valuable. Here we are creating mathematical models. We often have to make some assumptions. We might assume uniform material properties, perfectly rigid connections, or idealized boundary conditions. All are idealized mathematical models. While the simplifications are necessary to make the analysis tractable, they can lead to discrepancies between our predictions and the actual behavior of the structures. Factors like inherent material damping, how quickly material dissipates energy, can be notoriously difficult to model accurately. Similarly, complex geometries with intricate curves and varying thicknesses are real-world boundary conditions that are neither perfectly or near perfectly not possible to have in mathematical modeling. So there will be some significant uncertainties in our theoretical calculations. This is where the power of experimental model analysis shines. Instead of relying slowly on the potentially inaccurate assumptions, experimental model analysis allows us to directly measure the dynamic characteristics of the actual physical structures. Consider a scenario where a piece of industrial machinery is producing unacceptable levels of vibrations and noise. This could lead to what? It could lead to reduced lifespan, operator discomfort, or even safety concerns. Experimental model analysis provides a systematic way to diagnose the root cause, that is, pinpointing the source, by identifying the specific natural frequencies that are being excited during operation and visualizing the corresponding modes or mode shapes. We can able to predict how the machine is actually deforming. So engineers can pinpoint the source of the problem. Is it a resonance issue? Is a particular component vibrating excessively? Experimental model analysis provides the answers needed to develop effective solutions such as structural modification, isolation techniques, or changes in operating speed. Then there is the crucial aspect of validating and improving our analytical models, particularly finite element analysis model. FEA is a powerful tool, but its accuracy evenly depends on quality of the input and assumptions made. By performing experimental model analysis on a prototype or an existing structure, we can obtain real-world model data This real world model data can be compared directly with results from our FEA models. If there are significant discrepancies, it tells us that our model needs refinement. Perhaps we need to adjust material properties, update the boundary conditions, or even refine the mesh. The iterative process of experimental validation and model updating leads to much more accurate and reliable predictive tools, which are invaluable for future design iteration and optimizations.
Beyond troubleshooting exiting vibration issues and validating our analytical models, the insights gained from electrical model analysis are critical in other vital areas like structural health monitoring. Think about large critical infrastructures like bridges or aircraft. Ensuring the safety and longevity is paramount interest. Over time, these structures can experience wear and tear, develop cracks, or suffer damage due to various factors like fatigue, environmental conditions, or even accidental impacts. Traditionally, inspections have been done relied on visual checks, which can be subjective in nature, might not detect internal damages. This is where electrical model analysis offers powerful advantage to structural health monitoring. The fundamental principle here is that the model properties of the structures, natural frequencies, damping ratios, and mode shapes are inherently linked to its physical conditions. If any damage occurs, it alters the stiffness, mass distribution, or damping characteristics of the structure, and these changes will be reflected in its model properties. By periodically performing EMA and tracking these model properties over time, we can detect subtle but significant changes that indicate the onset of damage or degradation long before it becomes visually apparent and leads to catastrophic failures. Finally, we can also see that this electrical model analysis have a proactive applications like understanding dynamic characteristics of a structure before it's even built. It's incredibly valuable for designing vibration and noise control. Early in the design process, engineers can use analytical tools to predict natural frequencies and mode shapes of the proposed structure. However, to ensure that final product performs as intended and avoids undesirable vibration and noise, experimental validation is crucial. By building prototypes or even scaled down models and performing EMA, engineers can experimentally determine the actual dynamic behavior. This allows them to identify potential resonance issues where the structure naturally coincides with operating frequencies leading to amplified vibrations and to visualize mode shapes to understand how the structure will deform under vibration. This knowledge empowers engineers to make informed design decisions earlier stages itself. This might choose different materials with higher damping properties, modify the geometry to shift natural frequencies away from the excitation sources, or incorporate vibration isolation and damping treatments into the design. By addressing potential vibration and noise problems at the design stage, we can avoid costly redesigns and ensure a smoother, quiet, and more reliable final product. Whether it is a machine or structure, vehicle, bridges, or buildings. So, as you can see, this model analysis isn't just about fixing problems after they are occurred. It is a powerful tool that spans the entire life cycle of a structure from initial design and validation to ongoing health monitoring and troubleshooting. Its ability to provide real world insights into the dynamic behavior of complex systems makes it an indispensable technique in many engineering disciplines. Now that we understand the importance of analyzing the dynamic behavior of structures, as you can see, the key objective of dynamic testing is to understand how machines and structures deform when subjected to dynamic loads, particularly at the critical frequencies. Remember, critical frequencies are often related to natural frequencies. When a structure is excited at near or exactly at the frequency, then it is going to be the natural frequency. We can see the large amplitude of vibrations will occur and it will tends to deform at some specific patterns. Understanding this specific deformation pattern is crucial for diagnosing problems, validating models, and designing effective control strategies. Here, we are going to discuss about two approaches. The first approach is operational deflection shape measurements. We call it as ODS analysis. This ODS analysis focuses on characterizing the motion of a structure under its actual operating conditions. Imagine a machine running in a factory. This operational deflection shape measurements would involve observing and quantifying how different parts of that machine are moving and deforming. This technique is particularly useful for troubleshooting existing vibration problems. It also helps us to visualize how the entire structure or component is deflecting at a specific operating frequencies. The next one is model testing. This is very sound familiar to us. That is, we are closely related to our main topic, model analysis. In fact, model testing is the practical application of this model analysis. It involves deliberately exciting a structure with known input force and measuring its vibration response at various points. The goal here is to identify structure's inherent dynamic properties. Let us see in detail from the next slide onwards. As we are discussing the operational deflection shape measurements, our focus on understanding how a machine or structure deform under its actual operating conditions. The first point is this ODS measurements capture forced dynamic deflection shapes. What does mean? It means we are observing the pattern of deformation that occurs when the system is subjected to normal operating forces and it is vibrating at a particular steady state frequencies. This isn't about structure's inherent tendencies to vibrate in isolation. It's about its actual moving when it is doing its job. The steady state frequency is important here. We are typically looking at vibration pattern at a specific constant operating frequency, perhaps rotational speed of a motor, the blade passing frequency of a fan, or dominant excitation frequency within the system. The next point brings up a crucial limitation of this ODS measurements. They are valid only for forces and frequencies associated with the specific operating conditions under which the data was collected. This is a key differentiator from model testing. If the operating conditions change, for example, the rotational speed of a machine increases or a different external force is applied, the observed deflection shape will likely change as well. The ODS is a snapshot of vibration pattern under specific set of circumstances, not an intrinsic property of the structure itself. The third thing is, if a particular location shows excessive deflection, the ODS data can help us to identify the weak point. By visualizing the overall deformation pattern, we can pinpoint areas that are moving too much relative to other parts of the structure. This information can then guide us towards potential solutions such as stiffening that solution structures or the stiffening that particular location. So, to summarize, ODS, otherwise operational deflection shape measurements, gives us a picture of how a system is deforming while it is running. It is a powerful tool for understanding and addressing vibration problems under specific operating conditions. However, it is crucial to remember that the results are specific to operating conditions only. Next, important thing is the model testing. Any dynamic response of a machine or structure can be understood as a combination of its individual modes of vibration. Think of these modes as the fundamental building blocks how a structure will vibrate. Just like a musical chord, it is a combination of individual notes. The complex vibration pattern of a structure under any dynamic load is essentially superposition of its various mode shapes. What is the meaning of the superposition? We already seen in the last class only. If there is one frequency of running like this waveform, if another frequency like this, the superposition is going to be the output of these two waves. It will become like this. So the next important thing is mode. What is mode? It is characterized by specific natural frequency and its corresponding mode shift. That is, one mode will be one deflection pattern, another mode will be another deflection pattern. When structure is excited, it will tend to vibrate most strongly at or near its natural frequency, which is very much important, and each mode contributing to the total motion to a greater or lesser extent depending on the frequency and location of the excitation. The next important point is modal parameters. This modal parameters like mode shapes, modal frequencies, and modal damping ratio will completely describe the machine dynamics, which is a powerful statement. So the knowledge on this is very much important to describe the complete machine dynamics. When the forcing frequency of the excitation is closer to one of the system natural frequencies at resonance, that is, the response of the system exhibits a sharp peak at its amplitude. Think of pushing a child on a swing. If you push at the swing's natural frequency, even a small push can result in large oscillations. Similarly, in a mechanical structure, if we apply a force at or near a natural frequency, we will see significant amplification of the vibration response. The next thing is the phase of response changes by 180-degree as the forcing frequency crosses the natural frequency. For this, Imagine plotting the input force and the resulting vibration response over a time. The natural frequency response might be roughly in phase with the force. However, we can increase the excitation frequency and pass through a natural frequency, the response will suddenly shift, becoming significantly out of phase, almost an opposite motion related to the applied force. This phase shift is a key indicator that we are exciting a natural mode of the structure. Next important, very essential equipments are need an exciter to apply input force to the structure. This could be variety of devices we studied in the last video lecture, such as electrodynamic shaker that uses electromagnetic forces to impact controlled vibrations, or an impact hammer equipped with a force transducer to deliver a measured impulse, or even hydraulic actuators for larger structures. The key that we need to able to introduce a measurable dynamic force into the system. The next two things is transducer to measure resulting physical motion of the structure. These are typically accelerometers which convert vibration into an electrical signal. We will place this accelerometer at various points on the structure to capture its vibration response at different locations. The electrical signals from the transducers are often very small and need to be processed. This is where a signal conditioning amplifier comes in. It amplifies the weak signals from the transducers, filters out unwanted noise, and purposes them for further analysis. Finally, we need an analyzer equipped with suitable software. This is the brain of the operation. The analyzer takes the conditional electrical signals from the force transducer and the response transducer. The software then performs complex signal processing, often involving techniques like Fourier analysis to determine frequency content of the signal, identifying the natural frequencies, calculating the damping ratios, and ultimately extracting the mode shapes or modal parameters. So this combination of equipments allows us to introduce a controlled dynamic environment to the structure and precisely measure its multiple point response. By analyzing this relationship between input force and output vibration in the frequency domain, we can identify crucial model parameters that can describe structure's dynamic behavior. As we mentioned, the exciter what we use to introduce a controlled dynamic force into the structure we are testing. Let's start with electromagnetic shaker. That is, in this slide we are going to discuss about two things. That is the equipments what we need for giving the force or model analysis. First thing is electromagnetic shaker. The other thing is impact hammer, and we are seeing the difference between them. Here, the shaker will be used to the usually attached to the structure through a stinger to control the direction of the force. The stinger is typically a lightweight, a rigid rod that transmits the force from the shaker's moving element to a specific point on the test structure. Using a stinger helps us to ensure that the force is applied in a well-defined direction, usually along the axis of the stinger, minimizing unwanted moments or off-axis loading. Electromagnetic shakers offers a high degree of control over the frequency and amplitude of the applied force. They are particularly well suited for frequency function response testing, where we sweep through range of frequencies or excite the structure with specific frequency content signals like sine wave or random noise. Shakers can impart significant energy into the structures, allowing us to effectively excite multiple modes. They are commonly used for more detailed model analysis also. The next discussion is with respect to impact hammer. Here, the hammer have a built-in transducer in its head, that is a force transducer. This is a key feature. As we strike the structure with the hammer, the force transducer measures the magnitude and time history of the impact force. This impact generates a broad band excitation, meaning it excites a wide range of frequencies simultaneously. It is portable, inexpensive, and much faster to user than a shaker. You, you don't need to set up elaborate fixtures to attach it to the structures. Just you simply strike the point you want to excite. This makes it a very efficient tool for quick model surveys, especially on large or difficult to assess structures. However, there are limitations. Impact armors often cannot impart sufficient energy to effectively excite all the modes of a very large or heavily damped structure. Additionally, it is difficult to control the direction of applied force precisely. The input force is an impulse which may not be ideal for isolating specific frequencies as effectively as a shaker. So the choice between using a shaker and an impact armor often depends on the specific application, the size and complexity of the structure, the level of detail required in the model analysis, and practical considerations like probability and cost. Shakers offer more controlled and often higher energy input, while impact hammers provide faster and more portable solution for initial model surveys. The first key piece of equipment we need to measure the structure's response to the applied excitation is our transducers. As mentioned earlier, transducers convert physical motion into electrical signal that our analyzers can able to understand. Piezoelectric transducers are the most popular for vibration measurements in model testing. Piezoelectric materials have a unique property. When they are mechanically stressed or deformed, they generate a electrical charge or voltage proportional to that stress or deformation. Accelerometers, which are the workhorse of model testing, typically utilize piezoelectric effect to sense the acceleration of the vibrating structure. They are rugged, have a wide range of frequency, offer good sensitivity, making them ideal for capturing the dynamic response of a structure. Also, strain gauges can be used. Strain gauges measure the changes in electrical resistance of a thin wire or foil bonded to the surface of the structure as it deforms under stress. This strain gauges can be useful in understanding how a structure is flexing and experiencing stress during the vibration, and in specific model testing applications as such, where strain is the primary quantity. Once our transducers have converted the physical vibration into electrical signals, these signals are often needed to be processed before they can be accurately analyzed. This is where the signal conditions comes into play. The outgoing impedance of the transducer is often not suitable for direct input to analysis. Impedance is a measure of opposition to the flow of alternating current. If there is significant mismatch and impedance between the transducer and analyzer, it can lead to signal loss or distortion, resulting in inaccurate measurements. To address this issue, the change or voltage amplifiers are used to match the impedance and amplify the signal before analysis. For piezoelectric accelerometers that output a charged signal, charge amplifier converts this charge into a proportional voltage that is suitable for analysis input. Next, voltage amplifiers on the other hand are used with the transducers that directly output a voltage signal, boosting the signal level to improve the signal to noise ratio and ensure proper input to the analyzer. The heart of any modern model testing system is the analyzer. This sophisticated instrument takes the conditioned signal from our force exciter and response transducers and process them to reveal dynamic characteristics of the structure. FFT means fast Fourier transform. This is a powerful mathematical algorithm that allows us to decompose a time domain signal into constituent frequency components. In simpler terms, it tells us what frequencies are present in the signal and their amplitudes. This frequency domain representation is absolutely crucial for identifying natural frequencies of the structures. The next thing is analyzed signals are used to find natural frequencies, damping ratios, and mode shapes. What is natural frequency? We know. What is damping ratio? Also, we know. Let me see what is the mode shape. To determine the mode shape, the analyzers compass the amplitude and phase of the vibration response at multiple measurement points on the structure for each natural frequency. By looking at the relative motion at these points, the software can then animate or display characteristic deformation pattern, that is, the mode shape associated with that particular frequency. In essence, the analyzer acts as a sophisticated signal processing and analysis tool. It takes raw vibration data and transforms into meaningful information about structure's dynamic behavior. Here, this diagram provides a typical arrangement for performing experimental model analysis. You can see the physical structure here being tested at the top, connected to various pieces of equipment we have discussed so far. Notice how the structure in this example, a car body, is suspended using elastic cords. This is often done to approximate a free boundary condition, meaning the structure is relatively unrestrained in its movement. This allows us to identify its inherent modal properties without significant influence from external supports. Below this, you can see a exciter or shaker. This is attached to the structure via a force transducer. The shaker generates the controlled dynamic force that we apply to the structure at a specific point. Here, the force transducer is crucial because it measures the actual force being input into the structure. This measured actual force being the very important signal and that will be input to the signal processing equipment. On the structure itself, we can see accelerometer attached at different locations we discussed accelerometers are commonly used to measure the vibration response of the structure at various points. The signal from this accelerometer represents structure's acceleration at that location. Both the force signal from the force transducer and the acceleration signal from the accelerometer go to the signal conditioner. The signal conditioner, that is the power amplifier, as we learned, amplifies and conditions these weak electrical signals, ensuring they are suitable for input to the analyzer. The conditioned signals are then fed into the spectrum FFT analysis from the signal conditioners. This is where the magic of signal processing happens. The analyzer takes a time domain signal from the force response and transforms it into the frequency domain using fast Fourier transform. This allows us to calculate frequency response function which describes the dynamic relationship between input force and output vibration at different frequencies. Finally, we have a recording unit, that is our personal computers are generally computers connected to the spectrum analysis. This computers plays a crucial role in acquiring data, storing the frequency response function. It also typically runs the software that we mentioned earlier to further process frequency response function curve or responses to identify natural frequencies, estimating the damping ratios, and to extract and visualize the mode shifts. The diagram clearly shows how all the individual pieces of equipment work together in a coordinated manner to perform experimental model analysis. Each component plays a vital role in the process of exciting the structure, measuring its response, extracting meaningful information about its dynamic characteristics.